Yet the proliferation of debris risks compromising today's constantly diversifying satellite services. So all space agencies have to take serious risks each time they launch, including the European Space Agency.
If we are waiting for a situation where our uncertainty volume is completely empty, that would mean we could never launch. So believe it or not, we are launching despite of the possibility of having conjunctions with objects, because otherwise there would never be a green light for launch.
The risk is now proven and even quantified.
The odds of losing a satellite are 5%. Part of it is the risk of being hit by debris. The other parts are simple. There is complicated hardware that can break, causing the satellite to be lost. But the likelihood of losing a satellite can quickly reach 10 or 20% with the increase in orbital debris.
The European Space Agency estimates that the risk of collision will rise to 20% by 2038. So 1 out of every 5 satellites would not complete its mission. It's a huge figure. Space agencies have had to look at ways of negotiating this minefield and detecting the circling waste. Since 1957, the United States has been using a space surveillance network to predict where and when orbital debris will enter the Earth's atmosphere. They have established a catalogue of the debris that is currently in orbit and use this to determine which country owns the debris that is entering the atmosphere. They can also warn NASA if debris is at risk of interfering with their satellites. Over time, as the number of artificial objects in orbit has multiplied, this system has been refined and computerized. But in Europe, a similar space surveillance system was not put in place until 40 years later. In 1996, when debris from the Ariane rocket damaged military satellite Cerise, the French Ministry of Defense created a system known as GRAVE.
The GRAVE system, a space surveillance network, is our main sensor that allows us to detect objects that orbit around 250 to 600 miles in altitude, as long as they are large enough to be detected by radar. In other words, if they are the size of a large washing machine.
To detect orbiting satellites up to 600 miles above France, even when it's cloudy, the system uses a particular radar that makes real-time calculations to follow and anticipate the trajectories of thousands of satellites. The GRAVE system was able to detect 30 or so Chinese and American spy satellites that had not been catalogued previously.
Today, international relations in space are a mixture and an extension of those on the ground. In other words, there is as much mutual aid as there is competition, or sometimes open confrontations.
France agreed to keep quiet about the spy satellites, but in return, they asked the Americans for access to their orbital debris catalogue. This catalogue is considerably more detailed than the European version, since the Americans can detect objects as small as 4 inches.
We deal with the problem of small objects by Franco-American cooperation that allows us to retrieve information even at the confidential level.
This constant space surveillance is efficient and allows civilian and military satellites to avoid collisions with orbital debris. If there is a risk, ground-based operators can move their satellites slightly out of their orbit. These maneuvers happen more and more often, particularly for the largest satellite of all time, the International Space Station. This inhabited satellite is threatened by debris several times a year.
station has been on break for some info. We see the video view, and that does look correct.
To avoid orbital debris with an identified trajectory, the space station has to be moved from its course. In 2012, it avoided a piece of debris from the collision between the Iridium and Cosmos satellites 3 years previously. In 2021, the space station was forced to slalom 5 times between flying junk. This constant threat has become part of the astronauts' daily lives.
The space station is on a collision course with a small piece of space junk, as we've heard from the ground. My watch is beeping as a warning. We have to take the ISS into a higher orbit. For this, we have to turn on the engines for 37 seconds. And that is actually the only time in which we can measure or feel any acceleration on board. Suddenly, we are no longer weightless, but we are pushed backwards by the engines of the space station. So, let's start now.
Sometimes the ballistic data about debris is imprecise, in which case no risks are taken, and the astronauts are told to evacuate the station urgently. They take refuge in the escape module, which can be separated from the station and could return the astronauts to Earth.
Have a visual of the target. We are backing up. Well, so far, decent work. In 20 seconds.
But evacuation isn't necessary every time. Frequently, orbital debris is not detected if it is smaller than 4 inches. Nowadays, there are around 150 million pieces of junk that are too small to be tracked by radars. In order to avoid this menace, satellites and the space station need to be protected. In Freiburg, in Germany, scientists from the Fraunhofer Institute test shielding material using a superfast accelerator known as a space gun. This space gun fires tiny metal balls at various shielding materials. This series of chambers reproduces conditions in space. They are filled with light gases and accelerate the balls close to the same speed as orbital debris, 15,000 miles an hour. At this speed, the behavior of collisions is very different from that on Earth, during a car crash, for instance. When a car hits a wall or another car at 30 miles an hour, it is deformed, and thousands of pieces of debris are created as the material fragments. But at hypervelocity, speeds above 6,700 miles an hour, a collision creates different physical phenomena.
In hypervelocity impact, the particle is fragmented. So parts of it are vaporized and ionized, and the other parts can't withstand the really huge pressure loads which we have behind the shockwave.
In hypervelocity, a 1 millimeter ball has more energy than a baseball flying at 60 miles an hour. Reinforced doors protect the laboratory. The high-speed camera, which films more than 1 million frames per second, records the moment of impact. As a safety precaution, no one can stay in the room while the space gun is being fired. results of these tests on different satellite components are then analyzed.
For the International Space Station, we tested several shields, but we also try to test the components like space solar cells or components like tanks, which are located behind the walls of a satellite.
Using ultra-slow motion images, the Space Gun team manages to understand and model what happens during a collision. Their work allows them to come up with structures that are both light and resistant to hypervelocity impacts. They have just proved that doubling or tripling insulation layers can protect satellite components hit by debris smaller than 4 inches. The first layer fragments the debris. The second dissipates its energy and protects the third layer. Thanks to these experiments, scientists have been able to design satellites that are resistant to small debris. But even today, we are unable to protect astronauts when they are outside their vehicles during spacewalks. They remain exposed to small debris that can't be detected by radars or seen by the human eye since they are traveling so fast. Even a minor impact would puncture an astronaut's suit and lead to instant death. Because of this risk, NASA is actively developing robots that could replace humans to accomplish maintenance operations outside the spacecraft. Though even robots would be unable to withstand a collision with debris of more than ½ an inch. Obviously, the less debris there is, the better. Countries around the world have tried to establish rules for the non-proliferation of large debris, as they have done for land-based nuclear weapons. For example, satellite operators are asked to empty all fuel on board their space vehicles. All rockets are equipped with systems to vent or burn excess fuel, a system that is tested on the ground before each launch. Satellites are limited to a maximum 25-year lifespan in orbit. Finally, objects in low Earth orbit that do not completely burn up on re-entry are steered towards broad ocean areas for their final impact. However, these rules are not always respected, particularly since there is no governing body to police offenders. And as time passes, the amount of junk increases.
We're generating debris faster than it can clean out by the atmosphere. And that's what we refer to as being an unsustainable environment.